Welcome. Okay, Brandon, are you still unmuted? Oh, now we're out of it?
Yeah, we jumped out of the
Dang, flabbit. Guys, just 1 second. I just had to reset the mics. So that's what was up with that. So it'll give me just a second. And the mics will be reset. And we should all be good. Where's the add others info?
Yeah.
Well, it's because they literally redo the room like once every 3 days.
Sounds like how often we choose to.
Is this?
Zing.
Join now. So this should be closed. Then okay. Now mics are working.
Okay.
Now the mics are working. Wait. Yeah. If I talk, yeah, you can hear me on my phone.
Okay.
It should be working now.
Yes, I'll speak up real loud.
You should be good. Can you guys put in the chat if you can hear us now? Can you still? Okay, yeah. We're good.
Nice. All right, so.
Thank you so much. You didn't miss any important announcements, except for I will put in the chat the link for the Forge Slack. And anybody here can just ask me. Yeah, you're good. Go.
Okay. Cool. So I'm a Weave developer on DevX. Have experience in machine learning from my master's degree at BYU in the Perception, Control, and Cognition Lab. Most of my research there focused on using GANs for various data synthesis projects, as well as my current research focuses more on structural analysis of neural networks. That doesn't necessarily directly relate to what we're talking about today, but if there are any questions kind of surrounding that type of stuff, that's what I'm looking at. But let's go ahead and talk about the invention of a GAN. This is a really fun story. I like to kind of start off with this. So Ian Goodfellow, who published a seminal paper on Generative Adversarial Nets, tells the story about he was at university going to college with a bunch of friends, and one of his friends graduates with his PhD. So they go out to party, as you do, to a bar. They're hanging out, they're having a good time, and because these are deep learning PhDs, they start talking about deep learning questions, and one of his friends is working on a way to mathematically model pictures, and they get into this argument because Ian Goodfellow argues, that's too complex a space. You can't mathematically model an image that way, but he comes up with this idea of maybe creating dueling networks that will fight each other to end up with a generated image, and he thinks that might work, and they go back and forth. Neither of them agree with each other, right? Just having a fun time. Anyways, he gets home that night and he's thinking about this, and he's like, I think my friends are wrong. I'm pretty sure this will work. He's like, my girlfriend was asleep, so I just sat down and coded it up, and it worked first time, right? Which, if you've ever worked with GANs before, is incredible. GANs never work first time. It's crazy that it worked for him so well. So anyways, that's how GANs came to be, basically a drunken hangout at a bar and a slightly inebriated coding session. So if you ever feel like you're not contributing enough to your field, maybe go out to a bar and hang out with some friends, and that's a good way to improve your engineering prowess. So GANs, Generative Adversarial Networks, right? The term is something a lot of us have heard many times before, but as engineers, we really want to dig into the technical meanings of all of these words. English can be kind of a fluffy, floaty language, so we want to know exactly what we're talking about. So we're going to go through and really kind of nail down what some of these terms mean and how they relate to what we're trying to do. So the first term, neural networks, it's pretty obvious here at the ML meetup group, right? If we're talking about networks here, we're going to be talking about convolutional neural networks. We're going to talk about recurrent convolutional neural networks. Those are the two really big popular ones now for doing generative adversarial network type stuff. But the multi-layer perceptron, stacked linear layers, is where the GAN kind of starts. The original paper uses that more simple stacked linear layers. So any of these, really any network you can think of can be used inside of a GAN, but that's what we're specifically talking about here. So then we're going to talk about generative. What does that mean? So obviously, you know, generative content is when we're creating something, music, video, speech. If you guys have seen like the deep fakes or this person does not exist where you see a generated face, generated images of cats and dogs. Like those are all really popular, really fun things to pass around when you're talking about GANs. This is what we're talking about when we're talking about generative content. And there are a couple of caveats we want to add to that idea of generating content to kind of nail this more down. So first off, the content we're generating has to belong to the training domain. So we have a set of data, right? Images of cats or dogs. Maybe we have samples of biological molecules that we want to replicate. Maybe we have some music that we want to synthesize. And we want whatever we're generating to match in that set. According to human perception, this is kind of an interesting time where as an engineer, we're going to talk in terms of human perception rather than engineering models. So we want the generative content to match the training domain according to human perception. The next thing is we want to have a unique example amongst the training set. You can imagine, for example, passing a bunch of data to a neural network and it just memorizes, right? It basically encodes that data into itself. And then later you query it, kind of like a database, and it just gives you back the data that you've already fed it. We want to work really hard to try and avoid this because that's not really generative in the sense that we want it to work. Again, you can do this in other models, but for this specific instance, generative content is gonna require us to have something unique outside the training set. And then the last element here is we want a varied or generalized set of data. Again, you can imagine we create some sort of network that's generating content for us, and it does a really, really good job on the same thing over and over and over, right? Maybe it's speech synthesis and we're getting a single word, high quality, but it's only one word. Image synthesis, the same image over and over and over again. We don't really want this. We want something more broad, more generalizable. And so those are kind of the parameters we're going to be thinking about while we talk about generating content. The last item is adversarial. Again, this is a really popular thing that a lot of people who have talked about GANs have discussed before. It's this idea that you have two neural networks which are playing an adversarial game against each other. We formulate this idea of generating content as a zero-sum game with two mini-max players fighting against each other in order to improve the results. The outcome of that, well, so the two networks here, we call the generator and the discriminator. We'll dig a little bit more deeply into exactly what those look like, exactly what those are. But these are kind of like the basic things we want to really keep in mind when we talk about what is a GAN doing, what do we want our GAN to actually produce. So this is a really nice visualization about how that zero-sum game works. So if you think about a neural network, you can imagine there is this hyperdimensional space that is the loss function of that neural network. Here we're visualizing the loss as a 3D plane, or as a 3D surface. Doesn't necessarily, it's likely not going to be 3D, but for the sake of this visualization, it's easier to do it in 3D. And you can see, right, in a neural network, we're usually trying to do one of two things. Either we're trying to decrease the loss, find a global minimum, or we're trying to increase the loss, find a global maximum. So what a GAN does is it pits those two things together in an attempt to find a saddle point. So we are having one of the neural networks pushing that red dot down the slope. It's using gradient descent to move down. And then we have another neural network using gradient ascent to push the dot up to try and basically land on that saddle point, that very precarious middle section. And you can see now this visualization does a really good job of explaining why it is so hard to train a GAN. They're very finicky because this balance is precarious. If those forces aren't perfectly matched, you'll have a hard time getting it to settle into a nice saddle point. Okay, so let's go ahead, let's go through the process of building up a GAN. I'm not claiming that this is the way that Ian Goodfellow did it, but it's perhaps one path that you could take to arrive at the conclusion of the architecture for generative adversarial network. So first off on the left, we have an image data set called CIFR10. They're these little teeny images, 32 by 32 full color. They come from this paper, Learning Features from Tiny Images. Turns out these images, even though they're really small, are big enough and detailed enough that you can pull meaningful features out of there. In fact, you can see, like, if you look at the automobile row, those are recognizable as cars. Just kind of a fun little thing. And it's a small enough data set that it's easy to use for simpler models, right? It's a good way to test out your stuff and see if it's working. So on our left, we have a CIFR10 image, 3 color channels, 32 by 32. We pass it through a neural network, right? In this case, we're going to be using a multi-layer perceptron, but it's just layered linear layers, and the outcome of that is going to be a label, right? We're going to have a class. We're going to pass in, for example, an image of a horse, and we want it to come out with the correct horse classification, or an image of an airplane and have it come out with the correct airplane classification. And importantly, this label here, this 1 by 10 label, the way that it works is it's a one-hot vector. So if you guys have ever done, one-hots are really popular in hardware. It's this idea that rather than having an ordinal number 0 to 10, what we do is we have a vector that's 1 by 10, and then depending on what class you are, one of those lights up, right? So you have a 1 in the horse place, or 1 in the airplane place. That's a classic way that we're going to be classifying stuff in machine learning. Useful for a lot of mathematical reasons we won't dig into now, but just so you kind of have an idea of the structure of both the input and the output. Okay, so we don't actually want to do this though. We want to go the other way, right? The idea here is we want to create the cipher 10 image from some sort of lower dimensional thing. So the simplest thing to do here, right? Oh, real quick before we move on to that, some things to keep in mind about that structure. We're moving from a higher dimensional space, 3 by 32 by 32, down into a lower dimensional space. We're compressing that data. This is one of the reasons why machine learning is useful, right? This idea of we're taking this complicated image and getting some semantic, simple to process information out of it. We're compressing that. This neural network is going to undergo both a forward and a backwards pass. In the forward pass, we're going to pass all of the image data step by step through our neural network. We're going to arrive at a label. Once we arrive at the label, we're going to compare it to see how accurate it was. We'll get a loss signal. We're going to step that loss signal all the way back through the network. So it's a bidirectional network. Whoa.
I got it.
And the other thing is this network is going to generalize to unseen images, right? That's the nice thing about a neural network. I can train it on a set of pictures that I've labeled and selected, and then I can test it on out of set data, right? I can have it look at the real world and have it give me reasonable guesses for what's out there. The ability to generalize is an important factor of this network. Okay, so if we want to generate images instead of generating labels, we can simply just flip this network around, right? We just make the forward pass the backwards pass the forward pass. The data is passing through both ways. So instead of passing an image in at one end and then getting a label out, we pass our label in on one end and get an image out, right? And if you do the math with something like this, if you take a regular neural network and literally invert it, like the math will work out. So this is what will actually happen. So we're done, right? Like this talk is over basically. If this works, then everything is good. We can go home. But obviously, like it's not that simple, right? It's going to be a little bit more complex than just flipping that network around. And to understand why, we really need to keep in mind some of those caveats we talked about earlier, right? We want that final image to belong to the training domain. We have to have unique images coming out of this network that are not part of the training set. We want to make sure that the outcome is very generalizable. So there are some issues we're going to run into right off the bat if we try and just flip that neural network. The first problem, and this is the simpler of the two, is that a neural network is by and large deterministic, right? With the exception of some floating point funniness, most of what a neural network does is going to be fairly deterministic. So if we have, like I said, our 1 by 10 vector, and we light up that horse class, right? I'm showing an example here. And we pass it to our network. Even if we had a neural network which could reconstruct an image, every time we pass it that vector, we're going to get the same image of the horse. So we've already failed our condition of we want to have a variety of images coming out of this, right? We need more space to work with, basically, than our 1 by 10 vector gives us. Okay, and the solution to this, again, like I said, this is the easier problem. A lot of you have probably already hit on the solution to this. It's pretty simple. There are two basic ways we can handle it. The first is, well, let's just make that vector bigger, right? Let's just increase the number of elements in that vector so that we can hand more data to our network and get more examples of each class, right? The other solution is, well, we don't actually have to use it as a one-hot, right? Because it's now an input to our neural network, we could actually just pull it from a Gaussian, right? Sample from a normal distribution so that each element is a random number inside that bell curve, and use that instead. And in practice, this is what we do. We do both of these at the same time. We increase the size of our vector, and we sample that vector from a Gaussian distribution. We select numbers from a bell curve in order to pass to our network. This gives us much more space to work with, right? There's way more possible vectors now that we can pass to our neural network, meaning way more possible images we can get out. We do have the downside that classes no longer map nicely to our generated results, right? Before we could say, here's our horse class, give me a picture of a horse. Now we have to do something a little bit different. We kind of have to search the space to find a vector that matches with a horse. But it's not too much of a problem because there's this idea of spatially coherent results. A GAN usually is going to produce things that align spatially in a way that makes sense to humans. So what that means is if you find a horse somewhere in this vector space, right, you find a random vector that maps to a horse, nearby vectors will likely also map to horses. If you find one that maps to an airplane, nearby vectors will also map to an airplane. If you've ever seen some of those GAN visualizations where you can see the faces morphing and they look kind of similar, that's what's happening. It's the spatial coherence. So this is the solution to our issue 1. We want a variety of results, so we increase that Z vector, we sample it from a Gaussian.
Is there a reason you're using a Gaussian as opposed to just like random noise?
That is a great question that I think has yet to be answered in neural networks in general. Gaussians are used everywhere in machine learning, and in a lot of cases it's not well motivated. The idea is like, this seems to work well, so we'll pull from a Gaussian. There is this idea that Gaussian distributions, I think it's maximize entropy, and so it gives you the least amount of preconceived notions when you are passing this information in, right? You don't know, or you're not giving it any sort of bias in any direction, because a Gaussian is basically a hyperdimensional sphere.
I was just waving at Clint.
Oh, hey Clint.
Hi, why can you see me? Oh, I'm up there on the front. That's amazing. I'm gonna go ahead and mute or hide my camera so I'm not distracting. Sorry about that.
You're fine. Yeah, so basically it's this idea that a Gaussian has the least preconceived notions in it. So when you pass it, you're not biasing the network in any direction. It's kind of like the hand wavy argument. Okay, so the second issue, actually maybe I should stop. Does that make sense? What questions do we have before I move forward?
I think you're probably good.
Okay, I'm seeing some very studious nods.
Anybody on the video call have any questions? Because you can blurt those out too.
Yeah, we know that Clint gave us a good test to make sure that the audio is working on your side too. So. Okay. All right, feel free to like hit stuff up in the chat because the chat will pop up as well.
Well, it could. Keep an eye on it too.
Okay, yeah, Mariah will watch for your questions there.
Maybe I can ask a question then. So when you're talking about the Gaussian, is there something similar to, I'm trying to think what it is in scikit-learn, there's quantile transform. Is there something like that that you could use here that would do non-normal distributions?
Yeah, so I'm not super familiar with scikit-learn or what quantile transform does. Is that just moving, like reshaping your distribution, or how does that?
Reshape your distribution. So like it makes the center 50%, and then it does like the 1% is whatever the 1% would be. So it just kind of maps it into a normal distribution. Yeah,
so yeah, essentially any sort of method that you need to use to mush your Z vector. I mean, the nice thing about the Z vector is we're just randomly choosing it. So we don't really have to remap any data. If you just choose random numbers from a normal distribution, you'll be fine. So you could, like if you had, for example, say, Z vectors that you were selecting from some other distribution and wanted to like reform that into a normal distribution, you could certainly do that. In practice, it's usually just easier to pick a random normal distribution, like a random vector from a normal distribution. So,
Thanks.
And again, that prevents the bias from coming into the network. Okay, all right, so the next issue that we're gonna run into is a little bit more complicated. This is kind of the meat and potatoes of what a GAN is, and this is a really important question for any machine learning model is what should our loss function be? What should we do so that we can condition the results of our neural network, which we've just inverted, to produce realistic looking images, right? Because again, remember, we want realistic images, but we want realistic images according to human perception. So we have to think a little bit outside of the box because that's hard to define mathematically. We know that's difficult to define mathematically. And if we think about what would be an ideal loss function for this situation, right? This loss function is going to influence the output to look like a realistic image. So first off, differentiable, right? Whatever we use for our loss function has to be a differentiable function because we've got a flow gradient backwards through it. When we get our loss, we have to be able to backprop that so we can use the chain rule of derivatives to adjust the weights to arrive at learning. So differentiable is a must. Second, we would like our images we would like it to say images that are similar to the training set should have small loss, right? We want to have low losses if the image seems to fit in with the data we're training it off of, okay? The second thing is, or I guess the third thing at this point, is images dissimilar to those in the training set should have a large loss. And I have an interesting caveat. Even if they look good, we still shouldn't reward the GAN for giving us images that don't look like what we want them to look like, right? So if we have a set of cat images, we want the GAN to produce cats, not people. In practice, this doesn't tend to be a problem, but it's kind of like a nitpicky detail that is worth pointing out. We want dissimilar images to have large loss, and the similarity, again, should align with human perception. So this is a really tricky thing that we're doing here is we need to mathematically define something that aligns with how people see things. And we want to avoid, if at all possible, directly comparing our training set. This helps to prevent memorization because again, the last thing we want is to pass all our data to our network and it just memorizes things so it can just work like a database. Like databases are well studied, there are much better ways to do them than this, so we shouldn't just replicate something that already exists, right? We don't want to make a database. Okay. So as we think about this, and we think about, well, we want some sort of like way to classify images and see if they belong to certain classes. Like that sounds an awful lot like an image classification problem, which we already have a good solution for, right? Let's just use a neural network for that. And so that's where the second neural network comes in. Here, our neural network is literally our loss function. So we have our deep neural network, which is going to get generated images, right? And to start, those images are definitely not going to belong to the set of training data. And we're also going to have our training images, which definitely, by definition, do belong to the training data. And then we're going to have a classification which comes out here, and we're actually going to classify it in such a way that this turns into our loss parameter, right? This is our loss value. So images that are definitely training images have really low loss, and generated images should have really high loss to begin with. And the goal, eventually, on the top we have generated images, on the bottom we have training images, and you can imagine those two squares slowly moving horizontally into each other until they become one. That's the goal of the generator. It wants to combine those two such that the discriminator can't actually differentiate between the two. Okay. So this is our final architecture of our GAN. This is what we have ultimately, is our generator on the left, taking in that 1 by 100 Gaussian z-vector. We have an image which is created in the middle. We're going to pass that image through our discriminator, and then we get this bottom loss term, z of g of z. I think that's how that works. But that's our loss for the generator. And then we also have the term on top. We pass the training image through the discriminator to get the top loss, which is improves the generator or the discriminator's ability to differentiate between generated images and training images. So to kind of show you how the signal is flowing through this diagram, on the left or on the bottom we have z vector flowing all the way through to loss. Then we backprop all the way back through that line. And this bottom blue line is used to update the weights of the generator. Okay? Then we also on the top have training images moving through the discriminator. And we calculate a loss there. And then we backprop through the discriminator back to those training images. That's how we update the weights of the discriminator.
So is the comparison happening between the loss functions to compare the training image to the generated image? Or is it happening inside the discriminator itself?
So the comparison is happening inside the discriminator itself.
Okay.
The parameters of the discriminator learn to represent the training data, and that is what's used to condition the generated image.
Okay.
Interesting thing to keep in mind here, notice that the forward and back signals have to pass through this generated data. So we're actually literally moving our signal through our generated image. This means that we have to be able to pass gradient and signal through our image, so you can't model discrete data using a GAN. This is something that you have to be careful about or it'll catch you up. I've done this before. Discrete data is that one hot vector that we were talking about earlier. That's a very sparse data structure, lots of zeros in there. Discrete data tends to be very sparse. Sparsity tends to kill signal. So as you're moving backwards, you're going to get a multiplication by 0. That's going to kill all of your backward signal. You're not going to have enough information to update the weights. GANs don't tend to be good at training to produce discrete data for that reason, because really any sparse data set, you're going to have a lot of trouble generating with a GAN. How long does this go? 7:30?
I thought you want to stop.
What did the thing say so I don't bore you to death?
7:30-ish.
Okay, 9:30.
It says, I believe that the schedule on the meetup technically says from 6:30 to 7:15-ish.
Okay.
So it can go over, under, around, and through that number, but
Okay.
we're here to learn, so teach us.
Well, I think I'm gonna go ahead and I had some caveats to keep in mind, but a lot of those I can cover when we go through the actual code. So the last thing I want to point out here, if you've ever worked with GANs before, you probably haven't seen the two networks. It's because we usually just throw away the discriminator and the training set at the end of this training process. You don't really need them. So that's why you usually only see the generator as its own single network. We just chuck the rest of it. So I'm going to stop.
After it's trained, we chuck the rest of it?
Yes.
Okay.
Yeah. After it's been fully trained and this generator can generate realistic images, we don't need the discriminator
Because
anymore.
we're not training it. Yes.
Yeah.
That makes sense to me. I hope that made sense to everybody else.
Yeah, it's our last function, so we can chuck it.
Can I ask
Sorry.
a question about that?
Yeah, go ahead.
So when I think about transfer learning, if you're throwing the data away, you couldn't do transfer learning with it. Does transfer work well with GANs?
Sorry, define transfer learning for me really quick.
So like in a deep neural net, if you've already trained something before, you can eliminate like the first several layers and use the last layer, and then it makes your model. You can almost start using that existing, the parameters that you got from the previous layers. So it basically, you know what I'm talking about? Or?
Yeah, so I think that I understand. Usually in transfer learning, there's this idea of like moving from a large model to a smaller model by having the large model provide basically training hints for the smaller model. Am I tracking with you?
No, like when you create a model and you've kept all the parameters that you've run, and then basically you take like that model and then feed in all the data from your new model into that, and so it already does most of the hard work that you would have done originally.
I do it is a supervised learning, right? But the BERT NLP is a good example of that, right? So like Google published BERT, which is a series of rules to contextualize and understand, natural language. And then you can take that model that BERT is, pump that into a neural network, and it just becomes a layer in itself. And then you have additional layers gaining inference from the initial layer to then produce a better model for a specific use case, right? So it happens a lot when you have companies like Google or Microsoft or Facebook that are spending tens of millions of dollars to train, well, I don't know if that's, I feel like they spend that much, to train models. They then publish them, and you can take their published models, put it into your neural network. I don't know if you'd necessarily inject it as a unique layer, but that's how I like envision it, right? It then becomes a layer in your neural network that literally influences the outcome. It basically takes all of their hyperparameters from their training, and then you can make a new model out of that for your smaller subset of use case. Basically make sure you don't have to have all their data sets, you don't have to have all their inferences, but you can still get their results.
Yeah, so given that, you probably would be able to do something like that. You would maybe have to, I mean, you'd probably have to go and recover the training set, which probably wouldn't be that difficult if you've trained on some widely available training set for doing research type stuff. But yeah, if you don't have access to the training data, it might be a little bit difficult to perform. And I'm not sure that I really understand the question well enough to say you for sure could or couldn't. But I will say that it's worth investigating if you're trying to do something like that, because I doubt that it's completely impossible. There's probably some form that you could munge things into to get things to work.
Thanks. I didn't mean to get you off track. I just, when you said you throw the data away, I was thinking, I was just wondering if you could keep it, but yeah. Thank you.
Yeah, no problem. And again, like this is broad strokes, right? Normally, if anybody publishes any sort of GAN, they're gonna point you back to their training set. But like the idea here is you don't need the training image, because once you have a working generator, you just pass it that Z vector and you can get images out of it. So you don't need the training image to have the network work. Okay, are there any other questions really quick before we move on to the code? All right, let's go ahead and pull up some PyTorch code. So let's see here. So this is Google Colab. Oh good, it is showing up. Google Colab.
I love it. You can put corgi mode on and then have dogs running across the top. You don't have to. It's just an option.
Yes. So let's see, where is that? Oh, I can't even remember.
I'm pretty sure it's in like, I don't remember, settings. Was it in like literal settings of it? I forget.
Yeah, there is some, oh, it might yeah, literally be in the settings up here. Yes, it is. Okay, so you can go to miscellaneous. You can turn on corgi and kitty mode. These are important. I always program with mini power.
Because it gives you bonus points.
Yeah, it literally scores you as you code. But in more serious terms, Google Colab is a great resource. Google actually provides runtimes, so you're basically running a VM on Google servers. And it's really nice because you can come into this runtime, change the runtime type, and they'll give you access to a GPU. So if you're just getting into machine learning research or whatever, just come to Google Colab, select a GPU, and it'll let you train your stuff on a GPU much faster. So super great resource if you're just getting into stuff. This is an implementation of a GAN. And you can see, if you want to go and check this out afterwards, it's up on my GitHub. So BJ Akin, MIT license, go ahead and use it for whatever the heck you want.
Post that on the Forge Slack after. I'll send you a link if you're not on it.
Yeah, so it sounds like I'll post that afterwards. You guys can go check that out and have fun with it. There are some references here that I pointed to that I used when I was looking at creating this code. I would recommend you guys check it out too. This bottom link has a lot more than just regular GANs. It has Wasserstein GANs, Disco GAN, all sorts of interesting things. Because more modern GAN frameworks are going to give you probably better performance and will let you do some more interesting things. So you'll definitely want to look at that stuff if you want to implement a GAN for anything more recent. At the top here, we just have our imports, PyTorch. Torch Vision is a great module if you want to import some common data sets for testing, MNIST, CIFR10. I've used it for cityscapes before. It does a really good job of handling those standard data sets. NumPy, because we're in Python. Matplotlib is a great way to plot out your data, so it's super useful if you want to see the results of your training, loss curve, things like that. I like to do this a lot when I'm programming in PyTorch, especially for deep learning. Write little like mini cells that all they do is validate what you've just done, right? So here, all I'm doing is making sure that I can load in MNIST, that it looks correctly, that what I'm getting reasonably looks like a digit, that the size is what I expect it to be, right? So do that a lot. Machine learning is hard. Deep learning is really hard. So you just want to make sure that you're moving in incremental steps so you don't get all the way done with your network and find out that you have 800 mistakes and can't make any forward motion. Here's our generator, super simple. Like I said, multi-layer perceptron. I'm gonna give you guys a hint. This stumped me for literally like 3 or 4 hours. The batch norm, don't know why, batch norm has to go in front of the ReLU in a network like this. I don't have any idea why that is, but batch norm has to come first. So linear layer, batch norm, and then your activation function. If you do it the other way around, you'll just, stuff won't train. And you can see at the bottom here, I'm using a 10H. I noticed that other networks were using this. Just mostly improves numerical stability. 10H is going to make sure that the value that's output is between 0 and 1, I believe, which is the range we kind of want stuff for our pixels to be in anyways. So it's going to improve the results, give things a little bit more numerical stability, like I said. Make sure, as you're doing things, you're going to want to resize your inputs and outputs, because this is a linear layer network. So the stuff that comes out is going to be flat vectors, 784 by 1. You want to resize it so it's 28 by 28. And then you'll do the same thing. You'll see me do the same thing in the discriminator.
Does that mean that that's 28 pixels by 28 pixels, right?
Yes, exactly. Yeah, and if you look up here, you can see like that's.
No, yeah, I was just making. I thought you said 32 by 32 earlier, so I was just. Just making sure in my head that we were talking the same. Yeah.
Yeah. So I jumped data sets. CIFR10 is 32 by 32.
But
MNIST is 28 by 28. Yeah.
And this was MNIST number that you're the number set?
Yeah.
Okay.
Yeah, the classic MNIST digits. Again, you'll see here I've used a sigmoid. The reason I've used a sigmoid here is because we're using binary cross-entropy loss. You need the sigmoid for numerical stability. In PyTorch, there's also binary cross-entropy loss with logits that will do the sigmoid for you. But here, I just do it inside the network.
And the term binary cross-entropy loss, because that was a big word. That was literally like, big word alert.
So here's the good news. You don't actually have to understand it, because this is all that it is. BCE loss. It's a built-in loss function for PyTorch. We don't need to dig into the math or anything.
Is that the loss? So you're just saying essentially that is the loss function you chose for your GAN network.
Yeah. So.
Okay.
So earlier I talked about the discriminator being the loss function, and it outputs a loss. You actually have to use a loss function on the end of that as well to get the signal to back prop through.
No, because you have your discriminator and the loss. I see that.
Mm-hmm. Yeah.
So I'm just, you had the loss function at the very end, those little blue squares, and that's what I'm seeing that as.
Yeah, that is exactly right. That's correct. Let's see.
And that just happened to be the loss function you chose.
Based off
There
of.
are other loss functions.
Yeah.
Okay.
You could imagine using cross-entropy loss or like some sort of L1 or L2 loss, but BCE is what I saw used in other models. Seemed to work well, so that's what I adopted into mine. Right? Look at what other people are doing, because if there's one thing I've learned studying neural networks is that nobody knows what they're doing, so follow the guys that actually do. So go find other people's code that actually works and steal from them. Who was it that said like, good artists borrow, great artists steal? Go ahead and steal as much code as you can when you're learning this stuff, right? The reason I pointed out the sigmoid and the 10H is normally you won't see an activation function at the end of a network. It's a little bit funky, but in this case it helps with numerical stability, which is hard in GANs. Again, this is a step I always try and take once I've created my networks. I'm passing real data through, I'm passing the real images through the discriminator, I'm passing the Z vector through the generator, making sure that all the sizes match, making sure that everything that passes through works correctly. I'm making sure that the outcomes seem reasonable, right? Like I'm looking at these loss values and I say, okay, they're all somewhere between 0 and 1, none of them are negative, it seems like I've done things correctly. This cell alone, you'll catch so much stuff. Like you won't believe how many times you'll be like, oh shoot, I screwed up that sizing, that stuff is not moving through correctly, oh my loss value looks crazy, right? Just write a little cell like this once you have all your networks in place, pump data through them to make sure that they are kind of working the way you would expect. With GANs, it's super critical that you have some sort of function in place to visualize the results. So normally when you train a neural network, this doesn't matter as much because you can just see that loss continually falling. But remember that a GAN has this adversarial back and forth. Your losses are going to be up and down all over the place. It's going to be really hard to tell just from your loss how well your GAN is doing. So print out visual results so that you can see what's happening. You can see the results visually improve. If they're not, then you can stop it and go back and retool. So, and then also just a little thing when you're actually working with images, remember to unnormalize. Doesn't really make a difference here, but when we're working with full color images, remember that when we pass data into a network, we normally want to try and stick that into a more normal distribution, centered at 0 with variance of 1. If you didn't know that, now you know that. It will make your network train a lot better if you normalize your data. But when you want to go visualize the results of your GAN, you need to unnormalize that. You need to reverse that process. It's pretty easy to do. You can just look up simple equation online, but that will help make sure that you get the colors right. If you see super desaturated images coming out or like hypersaturated images, that's usually the easiest way to tell. Just like, oh, I need to unnormalize. So just kind of a little tip there that I've run into a couple of times. Here is the main training loop. Like Mariah talked about, we have our loss, we have our generator, we have our discriminator. We have both of our optimizers because we're optimizing the generators separately from the discriminator. We're going to pass through our data multiple times, training both our, right here, optimizer G-step. So we're going to optimize our generator. Then we're also going to optimize our discriminator, right? And these alternating steps as they fight back and forth. What you may have to do, and you'll probably see this in other networks, you might have to train your discriminator multiple times for every step that your generator takes. Does anyone have any ideas as to why that might be?
That was for my comment. You're good.
Oh. Any guesses as to why you might need to step your discriminator multiple times for the generator? Okay, if not, I'll just spoil it.
Spoil it.
The idea is the discriminator is handing back that loss signal, right? It is teaching the generator in a sense. And you want the discriminator to have a very clear picture of the differences between the generated images and the training images so it can hand back useful information. So the paper actually talks about training the discriminator to completion, basically making sure the discriminator has a perfect understanding of the differences. In practice, you usually don't need to do that. But if you ever see the discriminator getting updated 2 or 3 times, it's because we want really good signal to come out of that discriminator to help train our generator. So, and then I'll show you the results down here at the bottom. You can see when we start off, basically random noise, some white patches showing up, a little bit more coherent than maybe these random samples up here, but still not great. And then as we train, I trained for 200 epochs. You can already see stuff starts to get a lot better. And then here at the very bottom, like these are actually numbers, right? They're not like good numbers, but considering how small our network is, like there's recognizable 4s and 0s and 6s, some 7s. There's a wonky 8 right there, right? Like we're actually getting data out of this. So it works. It'll be really hard if you try and write one from scratch, which I wouldn't recommend. Again, go steal from other people, see what they've done. But it's going to take you a long time to get to this point because it is a really unstable process. There are a lot of little nitpicky things. David Wingate, who's the head of the PCCL lab, talks about like thinking really hard and really critically about every architectural decision you're making, because if you make a wrong decision here, it'll really trip you up. So be persistent, be willing to fail a lot, but in the end, you'll probably get something really nice. And I would use this. So if I wanted to, for example, do some sort of GAN research for a company where I was required to build something from scratch, I would start with something like this, regardless of what you're doing. In fact, this is how I started my research project at the PCCL. I got an MNIST GAN working. This is kind of the simplest possible version. You want to get the best possible results out of this to make sure your architectural decisions make sense, and then start moving forward. Increase the size of your network, mess with the hyperparameters to see how stuff goes. This only took a couple hours to train on a GPU, so it's fast enough that you can iterate on it, and it starts you at a point where you know things are working, which is really important. So I'm going to go ahead and call that quits for today. If there are any questions, let me know. But yeah, that's the talk.
Yeah, I told you the claps are so much nicer.
Yeah.
Does anybody have any questions?
Any last minute questions? I'll probably hang out for a bit if people want to ask them.
Oh yeah, you're welcome to hang out as long as you want. As long as I'm in the building, you can hang out. Clint would always stay longer than me, but you know, he doesn't work here anymore, so we don't care.
Sing!
Thanks for speaking. That was awesome. We'll be back again next month. We're in person. We always welcome remote. Remote's awesome. We're glad. Like, I felt like that was a really good experience to still get like their remote feedback. Like, it was pretty seamless. So thank you for coming. You guys here can hang out as long as you want. Grab more food. Ask questions. Yeah. And that's it.
Watch the Forge for the link to the...
Yeah, get on Forge Slack, and you can get all the links to the code. I'm going to turn off the meet, though. Bye, guys.
See ya.
Bye. Yep.